This is some pretty interesting stuff also. The applications of it are where things really start getting fun. But the concept of partial integration, it's like, I understand that this looks very intimidating, right? And actually, as you thumb through this packet, if you've already had a chance to take a look at it, you see things like spherical coordinates and so like, ooh, scary stuff. It's really not that bad because it's all grounded in stuff that we are very familiar with at this point. And partial integration, I mean, when you think about partial derivatives, what did we do? We held one variable constant and we differentiated with respect to the other. So we're just going to do the same thing, but in the reverse. All right. So when I find the antiderivative with respect to y of this multivariable function, all I'm doing is pretending that x is some constant. All right. So if that is the case, then this would just become a 2xy. All right. 2xy, because there's an understood y to the 0th attached to it. You're just increasing the exponent by 1 and dividing by the new exponent. Plus 1/3 y cubed. The only thing you have to bear in mind is that, yeah, we're integrating, which means that you have some integration constant that we call c. All right. No subscript necessary because it's just one integral. If you remember when we were dealing with, well, actually, I'm going to amend that in a second. You could just leave it as a c, but there's also another way you could represent it. But when we were dealing with vector valued functions, we had to distinguish one constant from another. This is not the same idea, right? Now, c could be some constant numerical value, but it could also be some expression that is just made up entirely of x. So what we could say instead, and again, I'm prefacing this by saying I don't really care. If you put plus c, that's good enough for me. You could say plus c of x, all right? Because this allows for any, so allows for any expression containing an x. All right, because if we're treating x as constant, then technically, I mean, I could add anything onto the end and it would still be fine as long as it's made up exclusively of terms involving x. So let's say, for example, I said my final answer was 2xy plus 1/3 y cubed plus the sine of x. Well, sine of x has a derivative with respect to y that's equal to 0, so that would check out. All right. So a little bit different, but nothing too crazy. So the other case, we're taking the antiderivative with respect to x. So we're looking at x squared plus y squared x, all right, because the y term is being treated as a constant. And then we would add c to that, but we could technically say c of y, because this allows for any expression containing y. Jeez, this pen just took a walk on me. All right, allows for any expression containing a y. Now we get to the juicy stuff. Now you remember earlier in the course I said that anytime you have a definite integral, you could just pop it in your calculator and call it a day. And we're all thrilled about that because in a lot of cases finding a definite integral is, it's aggravating because if you know that you can easily get the answer just by putting it in the calculator, why do we have to do all this work? Well, usually at that time I say, yeah, I let you off the hook with that because we make up for it with other topics. There's plenty of work to be done. So what does it matter if we do this one thing in the calculator? All right. So hopefully I said words to that effect. If not, I apologize. All right. What's going to happen here is, well, there's no double integral function in your graphing calculator. So you would not be able to just type this in. So what we can do, though, is kind of limit the amount of work that we have to do by hand, because we work from the inside out when we find a double integral or triple integral or quadruple integral, also known as iterated integrals. So an iteration is really just taking an answer to an operation and plugging it back into the operation to recompute, all right, and doing that repeatedly. All right, so what we're doing is we're getting this answer and then substituting it back in to the expression to continue the process. All right, so what I'm going to do here is I'm going to figure out this definite integral by hand, and then the rest of the way we'll be able to do it on the calculator. All right, so with respect to y, we're looking at 1/2 xy squared plus 1/4 x squared y to the 4th happening over the interval of 0 to 2. All right, so I'm just increasing the exponent of y by 1. So y had a power of 1, increased it to 2, divided by the new exponent. Same deal for the other one. I'm working around the x's, all right? So I'm not concerned with the x's. Then what I'm going to do is plug in. Now this again is with respect to y. So this 2 and this 0, these are for y. All right, so y is equal to 2, y is equal to 0. Now the 0 is not going to be relevant because I plug in a 0, that's going to go away. But if I plug in the 2, we'll get some unique values. So I plug in the 2, I get 2x plus 4x squared. All right, so that is my result for the first integral. Now all I want to do is integrate that with respect to x over the interval of 1 to 3. So you can see here that by carrying out the first integration, I now have a function that's exclusively in terms of x. Now it's calculator ready. All right. Now, granted, it's not. I mean, it's polynomial. You know, it's not difficult. You can do it by hand, but you don't want to have to do it by hand. All right. Especially since there are some problems that they could technically involve some pretty complicated stuff. I mean, we went over trig substitutions. That was one problem. It involved trig substitutions and also integration by parts. It was that one time, it was like a month ago, when we started the problem in class and it involved a secant, and I was like, okay, I'm gonna stop here and we'll pick up with it next class, because it took forever and we were kind of right at the end of class, right? It could be like that, but it doesn't have to be, because the first part of the problem, really, if you think about it, it's just a matter of working in terms of one variable, right? And so one of the tricks that I'm going to show you, a little trick of the trade, is kind of really cool. Is that if the arrangement of dy and dx is not to your liking, I'm going to show you how you can legally swap them. All right, you could switch the dy with the dx. There's a particular technique involved, and if you do that, you might make it for a more convenient integral. Something that maybe you would not be able to integrate prior to, but afterwards maybe you can make it very easy to integrate. All right, but as it stands right now, I can do this one by hand or in the calculator and not have any trouble whatsoever. So I just got to get my calculator out. So, I resume. So again, just a reminder, it's Math 9. We're typing in a 2x plus 4x squared on the interval of 1 to 3. All right, so 42 2/3. You can write it like that if you want. the math bracket, 128 in the, over 3. Didn't involve radicals, so math frac was an acceptable option. All right. So basically, it's kind of like I don't know how much you remember about synthetic division, rational roots and stuff like that, but I kind of compared this idea to that, where when you were working with synthetic division, your whole goal was to get it down into something that you can solve without using synthetic division, like a quadratic. You could use the quadratic formula, for example. Here, it's the ultimate goal to get it down to a single integral so that you can get away from having to do stuff by hand. All right, so you're just buying yourself time until you can just pop it into the calculator. So in the case of number 4, you look at that and say, well, okay, I got to do 2 things by hand. All right, because I got to integrate with respect to x first. It's always inside out. Now, if you're rightfully wondering why on earth we're doing this, like what's the purpose of this, stay tuned, we're getting there. All right. So here I see that I have a function contained within the innermost integral that does not contain a single x. That's beautiful. Because when I integrate this, the z sine of y, the integration is just that multiplied by x. Now that's happening over the interval of 0 to this disgusting looking 4 minus z squared. But regardless of how disgusting it looks, it doesn't have, it's going to replace the x within the function. So x is going to go away in a sec. All right? It's just things are going to get a little kooky. All right? So this is going to end up being, I'll write it in the cleanest way that I can, z root 4 minus z squared, and then that whole thing multiplied by the sine of y. All right. So then we're integrating this over 0 to 2 with respect to z, and then we're integrating that result over 0 to pi with respect to y. All right, so we haven't learned under what circumstances we could swap the variables. So at this point, we just have to grit our teeth and just get it done. All right, so, because this would be a lot easier if I could integrate with respect to y before I integrate with respect to z, because this would serve as a coefficient. Antiderivative of sine of y would be negative cosine of y. That would be nice. But unfortunately, the parameters are not in the order that I'd like them to be. And we haven't learned how to do that. And so we'll come back to this problem later on after I show you how to swap variables. And we'll revisit it and I'll show you how it could be a little bit easier. All right. But until we get into the visual aspects of this, there's no point in talking about it because it's not going to make any sense. Not a failing on your part. It's just I can't make it make sense without getting into the visual stuff. All right. So I'm going to rewrite. This guy over here is the same as saying z times 4 minus z squared to the 1/2 power. Now that sine y is going to be part of my final answer, or part of the next step in my answer, I guess. All right, because that's treated as a constant multiplier. All right. So this would be a U substitution problem, but I like to at least try to do U sub on the fly. The idea being that if I could save myself from having to define a U, to just rewrite an expression, to basically come up with an answer that I probably would have guessed to begin with, then like why not just take a shot in the dark? Right? So I know that 4 minus z squared to the 1/2, because U substitution is really just the shortcut to undoing the chain rule. All right, so if I were to find the derivative of an expression using the chain rule, then 4 minus z squared to the 1/2 would probably be in that. So what I'm going to do is anti-differentiate that part of it. I'm sorry, to the 3/2. So 4 minus z squared to the 3/2 power. All right. So then what I would do is just kind of test this out and see where it gets me. All right. So if I differentiate this, it would become 3/2 multiplied by this to the 1/2 times the derivative on the inside. All right. So, and you could just kind of scratch this out off on the side somewhere. You know, if I were to take the derivative, I'll just kind of chuck it over here. 4 minus, I'm going to erase it in a minute anyway. 3, just to kind of give you a look into the thinking behind it. I'd be looking at 3/2 times 4 minus z squared to the 1/2 times negative 2z. All right, the 2's would cancel, and my coefficient would be negative 3z times all that other stuff. I'll just rewrite it. All right. Now, none of this would be happening on paper for me. This is all happening upstairs. All right. So I'm just thinking, well, I don't want a negative 3z. I just want a z. All right. So what that would mean is that the coefficient of this integral, this result of the integration process, should be negative 1/3. All right. So, and that's just a correct for it, because I needed to get this, I got that, I want that to go away, so just multiply by negative 1/3. Right? So I can wipe out all that stuff, because that's all just side scratch work. Right? Because the reality is, if you're going to do any work for an integral, you might as well do the appropriate use substitution. The thought process behind that is that, you know, you take a shot in the dark, see if you can come up with what the antiderivative would be, and then go from there. And if it doesn't work, then that's when you call it quits and move on to you know, a different technique. All right. Now this is happening over the interval of 0 to 2, which is just wonderful news. All right. Well, yeah, it's news again. Maybe it's not wonderful news. It's just news, because the two works out beautifully. If I plug in a 2, it's going to 0. All right. It's just in this case, when I plug in the 0, it goes to, well, potentially something else. All right, because we're integrating with respect to, or we integrated with respect to z, so that's the only thing we're substituting in for. All right. So all I have to do is plug in the 0 for z, and I'll get my results. So sine of y, it's subtraction of a negative, so that's going to a positive. 4 minus 0 is 4, to the 3/2 is 8, so we're looking at 8/3, right? So sine of y times 8/3. So the last, that should be a pi. The last integral we have to count for is the 8/3 sine of y with respect to y. And that you can even do by hand, because like I said, working with trig functions, that's specifically sine and cosine, that's super easy, barely even. Right? So I'm going to get sued for using that comment over and over again. So negative 8/3 cosine of y on the interval of 0 to pi. All right, so negative 8/3 cosine pi minus negative 8/3 cosine of 0. So we're talking 8/3, because cosine of pi is equal to negative 1, plus 8/3, because cosine of 0 is equal to positive 1. So result is 16/3. right. So that's one funky looking iterated integral, but conceptually there's nothing new there, right? So it's just a matter of carrying out the process. And the only sticking point is actually finding the antiderivative in the second, for the second iteration. Once you do that, it's home stretch. And I only opted to do that last bit by hand. You just pop that right in the calculator and get 16/3, it comes out clean, right? It won't always come out clean, but I accept decimal answers anyway, so what does it matter, right? Exactly. Now, number 5, I'm exercising my teacherly right to do all the easy ones in class and then leave a hard one for you to do on your own. All right, so I'm putting a star on that one. And again, just like the other Lagrange problem, it's only for the purpose of you giving it a whirl first before I take you through the process. All right. What I have now, just looking at the relationship between dy and dz, I have the ability to swap these because these correspond to a rectangular region. All right, this part of it, the x, that doesn't seem to be relevant because we've already accounted for that by the time we get to this step. All right, so when we're in this step here, we could have actually swapped the dz and the dy only because this corresponds to a rectangular region. And how do I know it's rectangular? Well, these are constant values. I'm going from a z value of 0 to a z value of 2. All right, so those would be two parallel lines. All right, we're going from a y value of 0 to a y value of pi, so two parallel lines. Intersect them and you're going to have a rectangular region. All right, so what I can do now is I can go back to that problem as promised, and we can swap the boundaries of integration. Same function, so z root 4 minus z squared times the sine of y, but this time I would make it, instead of dz dy, I would make it dy dz. All right, so that allows me to just integrate this mamma jamma here. All right, so when I'm integrating this part, I don't need use substitution or anything even remotely complicated. I'm just integrating the sine of y, which is negative cosine. So I'm looking at negative cosine of y times z times the square root of 4 minus z squared over the interval of 0 to pi. So once I crunch those numbers, things are going to start cleaning up very nicely. And then we'll be done with the problem in seconds flat. All right, because if I plug in a pi, I'm going to get a negative 1. So positive 1, so just z root 4 minus z squared. Plug in a 0, I get a negative 1, so minus the negative variation of this. Which is going to give me 2 of those, so 2z square root of 4 minus z squared. And that's happening over the interval of 0 to 2. Now you might say or think, wait a minute, I still got to do use substitution. But you're neglecting the one critical component of this. Once you get it down to a single integral of one variable, it's a calculator problem now. It's no longer a by hand situation, all right? So, I had to use substitution. And if it wasn't as simple as that, then maybe I would have had to do something else, like partial fraction decomposition or something crazy. Here it's the same type of integral, same difficulty level of integral, but now I have the ability to use my calculator. So swapping the boundaries, incredibly not only useful idea, but also in a lot of cases necessary. And what I always do, and this is something I could definitely back up because I've done it already. instead of making those the promises that I don't always remember to cash in. So anyway, math, enter. I always put on the test a 16/3, much easier. Right? I always put a problem on the test where it's impossible, at least from our perspective, based on the knowledge that we have, impossible to find the antiderivative one way, but very easy to do it the other way. Right? So it's one of those where if you try to work with it in the given form, no way you would possibly get the result. But when you swap the variables, and it won't be a simple case where the base region is rectangular. When you swap the variables, it becomes very easy, like very, very easy. Instead of describing it, I'll just show you. Digital link. Blurry. Huh. I'll bring it in. Alright, so number 7 on the previous version of this test had the iterated integral where the innermost function was the inverse sine of y. Alright, so what happens is people try to fake their way through this solution, and in some cases they actually think that they know the right answer, because what happens is they get the derivative and antiderivative of inverse sine confused with one another. So if you remember that the derivative of the inverse sine is -1 over the square root of 1 minus x squared, or in this case y squared, congratulations, it is of no help in this situation. All right. That's not entirely true, because if you know that fact, you could use integration by parts to help you figure out what the antiderivative of that is. But you can see I have a variable upper bound here, so another technique that we're about to learn comes into play. But if I'm able to swap dy and dx, now this is just treated as a constant. Its antiderivative is x times the inverse sine of y. At which point, chuck it in the calculator, call it a day. All right, so you go from something that would take like an entire page to do, you go from that level of difficulty to something that's like, I can't believe I ever thought this was difficult, right? It's that much of a disparity between the two ways, right? So I always put a problem on there like that, and it will be number 7, right? So the way the test is structured, you know, I put 2 versions up because I had a really large class in the spring and a lot of people with rolling eyes during the test. I had like a solid 35 people in the class, and there were a bunch of people that were like clustered together, and they were trying to share answers, but you know, you get them a couple of times when they copy down the answer to the wrong version of the test. You know, it's always nice to see. But yeah, so I have 2 different versions of the previous unit test for this unit. So definitely plenty of opportunity to practice. But you can see, you know, a temperature function, a little gradient action. You know, you got that bad boy right there. You got some volume questions. You know, you got a proof. So definitely something you can even start working on it now, because if the first one's a directional derivative, absolute max and mins, we've worked on that already. Critical points on second derivatives test, Lagrange. I like saying that, as you can probably already tell. This is the gradient question. The volume stuff we're not ready for. After class today, we'll be ready for any kind of iterated integral. But basically anything that involves volume and area, we're not quite there yet. But you can start making some headway on this. You know, so definitely something to keep in mind. All right. So, continuing on. So now we're going to talk about the why as opposed to the how. And actually, we're going to kind of get into the idea that you've been working with double integrals for a long time already. You just haven't realized it. All right. So that's kind of a strange thing to think about, because it's like, how on earth could that be the case? Because I have never seen that double integral symbol before. Yeah, I've taken the antiderivative and then taken the antiderivative again, but that didn't mean what this is about to demonstrate that it means. All right, so we'll see. Now, what a double integral gives us is actually, and you look at the Riemann sum variation of this, is giving us the volume over an interval, right? Areas and volumes, depending on what you're looking at. So if you look at the diagram, basically what you're getting when we find the product of dx and dy. So the notation here is a little bit, I would say, on the noisy side. So let me just kind of streamline it a little bit. Right? We're looking for infinitesimal length and width. Right? So what we have here is some function that we'll call z that has a height. All right? So that's my z function. Then we also have some length in the x direction, infinitesimal length. So we call that dx. We also have an infinitesimal length in the y direction, which we call dy. All right? So what we're getting at here is that the volume contained between a three-dimensional surface and the xy plane would be z, it's length times width times height. So it would be z multiplied by dx by dy. All right? Or the other way around. All right? You could say dy dx.
So it could be like z could be like a function for like a wave, and you can figure out like the volume of like the waves on the ocean.
Exactly. Yeah, so as long as you have a function that represents the surface wave, like what it would, the path that it would be traced out on the surface, then you could figure out the volume over a square interval or square region. All right. So what we figured out is one rectangle with infinitesimal width. All right. So I can sketch this out a little bit. Yeah, it's not quite in my wheelhouse, as we know, but it's something. So we would have this rectangular prism. That actually wasn't half bad. All right, this rectangular prism, I mean, it's drawn with thickness, so it makes it seem like it would actually be like a matchstick. But it's really not. It's of such infinitesimal dimensions that it would be imperceptible, right? Or imperceivable. I don't know what the right word is. Anyway, so what we would have to do is collect every single one of these infinitesimal distances along the x-axis. And we do that by integrating. All right, if you learned anything about Riemann sums back in Calc 1, it was the idea. Now, there's a lot of hand waving in Calc 1 related to it, because it's just it's a concept that people don't often enjoy teaching, so they kind of skip over it a lot. But the origin behind the integral, the definite integral, comes from the collection of all of those infinitesimal distances. All right, so if you're looking for area, you find a little teensy tiny sliver of a rectangle, find a function model for that teensy tiny sliver of a rectangle, and then integrate all of those rectangles together to give you the collection of total area. All right, so that's what we're going to do here, but we're going to do it for both the x dimension and the y dimension. All right, so I would need a double integral. All right, so an integral to account for the x dimension and an integral to account for the y dimension. And z, I don't need infinitesimal distances, because what's going to happen is, as we project those infinitesimal x's and y's up into the z, it naturally creates the sliver of z that we need. For each one of the x's and y's, we get a corresponding sliver of z. Right? So we don't actually have to manufacture that. We could just use the z function itself. Right? So the same idea holds if the order is reversed. So we get to our first real connection here, and that is that if you have a square, or sorry, not even square, rectangular base region, then the order of integration is irrelevant, right? So that's telling me that if my rectangular region, or my base region, so the region corresponding to the surface, but on the xy plane, if that's a rectangular region, then it doesn't matter if the dx comes before the dy or vice versa. It's when it's a non-rectangular region, that's when we have to do something different, all right? So in the case of that previous example, so basically everything on this page is really just addressing what I was just talking about, all right? So it's a lot of textbook jargon with really not much payoff. All right, so I'm going to take you through an example, a juicy example here. And if you look, I mean, I don't know how, it's probably not that good on your papers, but the traces of the graph or the wireframe is often more useful than the actual shaded version of a surface, right? So you can kind of get a sense of the parabolic nature of this curve here just by looking at the wireframe, right? So, like, what's that?
Actually came out.
Oh, it did. All right, cool. Every now and then, you know, a broken watch is right twice a day. So, what we want to do is find the exact volume of a solid bounded by the surface given, and then we have a rectangular region, a rectangular base region. So that tells us that we're going to be able to swap our boundaries. Our variables of integration. All right. So, but what we want to do is start to develop a little bit of an intuitive understanding of why on earth we're doing this to begin with, right? Because what I've experienced both as a student and as a teacher is that for this particular topic, as well as volumes in Calc 2, that people start to kind of rely on, all right, here's a rule. I'm going to put in some numbers. I'm going to put in a function. I'm going to hit enter on my calculator and hope it gives me an answer that isn't ridiculous, and then move on to the next question. All right? We're trying to avoid that sort of thing here, and hopefully we can do that. All right? So we want to be parallel to the YZ plane. All right? I didn't really make that part of it as obvious as I could have, but here's my Y, and here's my Z plane. The Z plane is easy enough. All right? So parallel to the YZ, so we're talking about this corner here, so this surface. So basically anything that follows this orientation, right? So I'm going to use the wireframe to my advantage here. I'm going to bring it in a little bit. I'm thinking I already have red. I'm going to go with purple. I'm going to go with red. Clean miss. Yellow? Yeah, red sucks. Back to the yellow. Oh, yeah. Oh, look at that. That's pretty good looking right there. All right, so I'll bring it all the way down, even though this is not actually how the graph would look. I'm going to bring it all the way down and create a little slice. And that slice is going to have some thickness. This is related to the technique of finding volumes by cross sections in Calc 2. And so we're going to kind of rely on some of that knowledge. Right? So the topmost part of it, I'll shade it in. All of this bit of stuff here That's all along the surface. All right, so this is on the surface of the function. All right, so its height is determined by whatever the function is. So I'm gonna just call that z. All right, the thickness is along the x-axis. So that's gonna have a thickness dx. All right. So if I want to find the volume of this whole shebang here, all I would need would be a length y. All right, so that's going to be going from the x-axis out to whatever that value of y is. It's hard to see, but I think it's 6. So that would correspond to this distance here. All right. So what I would be looking to do is multiply y by dx and then multiply that by z, and then we would pretty much have it. But the issue is I can't actually multiply the entire dx by just a y, all right? Because what's happening is I have little infinitesimal distances here that are going out along the y-axis, all right? So collectively, they give me that distance y, but each one of those little slivers, and I'll just draw an arrow to one of them, I guess, would be a dy, all right? And so what I want to do is collect every one of them, because remember, I mean, and drawing the diagram is a nightmare, but if you think back to the previous page, we had those rectangular prisms that ended up giving us the volume. So what I'm looking for is a rectangular prism that has dimension dx and dy that projects up into the surface, the edge of the surface. All right, so each one of these little slivers we could think of as a dy. If we collect them all together, then I would have my function. All right, so what I'd be looking at is z dy, it locked me out, dx. All right, and that would be happening. So the y values, you know, I'm not going to scroll back up, but I think it's pretty straightforward. It looks like my y values are spanning from 0 to 6, and my x values are also spanning from 0 to 6. All right, so so if we collect all of the dy's underneath this curve, what that's going to do is it's going to give me a y. So let me show you what that looks like. So we carry out this process of integrating. That first calculation gives me just a zy on the interval of 0 to 6. All right, easy enough. All right, I'm not actually going to put the z in until I need to. All right, and I don't need to yet. All right. But if you remember, what I was saying before is that what I wanted to do was take that entire distance, that horizontal, well, not really horizontal, but you can kind of think of it as horizontal, depending on your perspective. But the distance along the xy plane parallel to y, we wanted that entire distance y, where y was equal to 6, because we knew that that was not going to change. But sometimes it does change, so we want to be flexible, all right? But ultimately, by finding the antiderivative, that's what happened anyway. By finding the integration or integrating z over the interval in terms of y from 0 to 6, we got z times y, which is precisely what we were looking for anyway. All right, so intuitively, that's what we would have come up with, but in the act of creating an iterated integral, it worked itself out. All right, and so what we get here is 6z over the interval of 0 to 6 dx. All right. Oh, sorry. Back it up. Just back it up. Just back it up. Back it up. At this point, we have to plug in the z function because z does have a y in it. We have to make that substitution. All right, so z is equal to x squared sine pi y over 6. Oh, dang. I needed to even substitute it in earlier. All right, well, I proved my point with the whole integration thing. Now I'm going to use a technique that I like to call the right way to answer the question. All right, so 0 to 6, the z, battery's low, it's one of those days. So again, x squared sine pi y over 6. So x squared sine pi y over 6 dy. All right, so maybe not as easy as I was making it seem, but we'll get there. All right, so integrating really only involves me messing around with this component because that's the only one that has a y in it. All right, so negative x squared cosine pi y over 6, but then I have to divide by the inner function, which would be the same as dividing by pi over 6, which is multiplied by 6 over pi. I liked it better when it was just a z. All right, so plug in the 6. We're looking at negative x squared, because it's still with respect to y, cosine of pi times 6 over pi minus, I'm going to do the same thing, but then I'm plugging in a 0. So negative x squared cosine of 0. Yeah, but we're dividing by the derivative of the inner function. So dividing by pi over 6 is the same as multiplying by 6 over pi. So we're multiplying by the reciprocal. If we were taking the derivative, we would multiply by pi over 6, but it would go in the other way. All right, so we're looking at, well, this is going to go to a negative 1, so we have 6x squared over pi. These two will become positive. So cosine of 0 is 1, so plus another 6x squared over pi, which is going to be 12x squared over pi, but I'm going to write it as 12 over pi x squared. All right, so then we just have to integrate that with respect to x. And so that you could chuck in the calculator, but you also don't really need to because, again, it's pretty clean. Because the part that was making it difficult was the presence of the trig function, but now that's gone. We've swapped it out for a constant multiple. So, and one thing that I would recommend, because we came across this, I think, last class, where if you leave the pi in there, then you're going to have an answer that's a multiple of pi, so you're going to get an ugly decimal. But if you pull out the 12 over pi, anti-differentiate, even in the calculator, let the calculator do the work, and then just multiply by the 12 over pi later on, you get a cleaner answer that way. But I'm just going to do it by hand. So x to the third, we're dividing by 3, so 4 over pi over the interval of 0 to 6. So we're looking at 6 cubed from my experience in statistics is 216 times 4. So we're talking 432, 6, 864? 864, yeah. over pi. So, you know, a fair amount of computation, but again, that last step didn't actually have to be done or completed by hand. It's just a matter of, you know, just picking and choosing your battles. All right. Now, if you go the other way, so you swap your variables of integration, then you should still get the same answer, but you're going to get a different diagram. Right, and so I'll draw the diagram, but I'll leave it to you to try that on your own. All right, so when I draw this diagram, I'm looking at something that would come across, you know, something like that. Now, I'm just kind of working off of what I have here. You know, it definitely goes up and has a maximum at some point, but you know, it makes it seem like it's chopped off at the top, but it really doesn't matter what it looks like on the high end. It's what matters is what it looks like on the low end. So we have something along these lines. Now I'm going to span out in the direction of x with each one of these representing a dx. All right, and here's my dy. So when I didn't get a y in there. And we definitely know that the height of the surface is going to be equal to z, some variable z. So what we can do is collect each one of these slices. So we did it with respect to y first. So now what I'd be saying is that I'm taking my z function, multiplying it by dx dy, and integrating the x component over the interval of 0 to 6, followed by the y component also over the interval of 0 to 6. All right, so that's your setup. All you have to do is just carry out the process, but don't do what I did. Remember to put the z, the x squared sign of whatever it was, in for z before you get started. Otherwise, bad things are going to happen. All right, so all of this is really just introducing what's known as Fubini's theorem. It tells us that the order of integration is interchangeable, but not always easily interchangeable. All right, so if it's a rectangular base region, it's easily interchangeable. You just swap your boundaries of integration and you swap your variables. But if it's not a rectangular base region, then you got to do something different, which is the subject of the last thing that we're going to cover today. All right, so we're going to move on to that in a second. Let's do this real quick before I forget. So what if the region in the xy plane is not a rectangle? Funny you should ask that. So we have all these rules, all these fun rules, linear combinations of double integrals and all that good stuff. The linear combination stuff is really just telling us that just like with definite integrals in single variable calculus, you can break apart different bounded regions, find their areas and volumes, and then add them together later on. Right? You don't have to just do it over a finite interval. Right? So that I don't think is anything new. Right? I mean, it's definitely not anything new. But let's hop on over to page 75 and tackle a case where we have definitely a region here where it's bounded by curves on the base area rather than linear functions making it a rectangular base area. Right. So we know that we have some function z. Now it's represented as f of x comma y, but that's okay. Z is equal to x squared plus y squared. We know that dx and dy is going to give us a product that when multiplied by z is going to give us ultimately the volume, all right, contained underneath the surface. a lot of this is just going to boil down to problem solving, because sometimes they'll want the area or volume contained within the figure, and sometimes they'll want the volume between the figure and the XY plane. Like in this case, it's saying bounded by the curves in the XY plane. So it's suggesting that we only care about the volume outside of the surface but above that non-rectangular base region, which is fine, because that's what a double integral gets us. It always gets us the volume contained between the XY plane and the surface that we're interested in. But if I wanted something like the volume contained within the figure, then what I'd have to do is something a little bit more complicated. I'd have to find the volume surrounding it and then subtract all the excess volume that I don't want. That's way more complicated and really a subject or a conversation for a different day. All right, so I definitely don't want to rush into that, because it's a lot more thinking involved. All right, so what I want to do is set up my double integral. All right, so I have my z, and pick your poison. It could be dx dy or dy dx, but once you make the commitment, you have to stick with it. So I'm going to say dy dx. So I'm going to go with a double integral dy dx. I don't need it to be that far away. All right, now my bounded region varies depending on where I am along that bounded region. Okay, so what I'm going to want to determine is what the relationship is between these two parabolas, because definitely they're opposing parabolas in order to capture that bounded region. So I'm going to need to find the intersection of those two. So I'm going to set the y function of 1 minus x squared equal to the other y function, x squared minus 1, and solve. All right, so I'm getting 2x squared equals 2, making x squared equal to 1, making x equal to plus or minus 1. All right, so now I know my boundaries for x, which is great. So then I'd ask myself, well, what are my boundaries for y? Well, what I'd want to do is take a look at my base region, but only in the xy plane. All right, so I'm going to draw a quick sketch. And, drawing quick sketches is not always what people have in mind. You just want to be able to jump right into a problem and start solving it, but a good sketch goes a long way. All right, so what we're dealing with here are two, like I said, opposing parabolas. If you remember from Calc 1, so this is y equals x squared minus 1. Y is equal to 1 minus x squared. If you remember from Calc 1, when you're finding the area between two curves, what we did was you took the dominant curve and you subtracted from it the non-dominant curve. So the one that was physically above the other. That's when you were looking from the perspective of the x-axis. But if it were from the perspective of the y-axis, it was the rightmost curve minus the leftmost curve, as long as there wasn't a change in dominance. So here, the blue curve for the relevant region is always physically above the black curve. So we're in good shape. If there was a transition where the black curve was physically above the blue curve, like in the outer fringes here, then I would have to account for that, but that's irrelevant in this case, because I'm only looking for the region between the x value of -1 and the x value of +1. All right, so the difference between those two values would help me find the area, but really all I just need to do is define my double integral based off of the lower function and the higher function. So the lower function of x squared minus 1 would go here. The higher function of 1 minus x squared would go here. Because it's physically higher, so it actually takes the higher location on the integral. So the one that's physically higher graphically is physically higher within the integral. All right, so it's going from, so in terms of y, it's going from vertically y equals x squared minus 1 to y equals 1 minus x squared. All right, and then the x values are spanning from -1 to 1, and so now we have our double integral. All right, so if you're dealing with a non-rectangular region, you have really two integrals that you're going to be dealing with. The first integral is the one that should contain the constants. The second one, well, the one that you would do first would be like the one that you would write the second. That one should be the variable function, or the bound should be variable. So the outermost integral should be the one that contains any constants. So it's kind of like a composite function where we're saying that y is equal to x squared minus 1, y is equal to 1 minus x squared, where x is equal to -1, x is equal to +1, or anything in between. All right? So with that in mind, we can go through this process, but you got to be cautious, because if I got it backwards, then what I would do is I would create too many constants within the double integral too early, and it would mess everything up. And we'll talk about why that happens the way it does next class, but it has serious consequences. All right, so my double integral is going from -1 to 1, then x squared minus 1 to 1 minus x squared. The z function is x squared plus y squared, and we're integrating with respect to y first and then x after that. All right, so we're looking at x squared y plus 1/3 y cubed over the interval, so this is where things get weird, x squared minus 1 to 1 minus x squared. But all we have to do is substitute those functions in everywhere I see a y. So x squared times 1 minus x squared plus 1/3 times 1 minus x squared cubed minus all that same stuff, the same structure, just this time replacing the y's with x squared minus 1. All right, so minus x squared times x squared minus 1 plus 1/3 times x squared minus 1 as a quantity cubed. And you're like, this is outrageous. Why are you doing this to us? It's because I don't like you. No, this is a wonderful class. I actually enjoy this class. It's just, it is what it is. Look at this. It's terrible. Look at all that. That being said, it's really not as bad as it could be, because we succeeded in our mission. Our mission was to get down to a single integral that contains only one variable. So regardless of the fact that this is as ugly as sin, it's still something that could be typed into your calculator. All right? You can clean it up if you want. That should be a minus. No, it should not be a minus. I just got to close parentheses. All right. So this is something that could be typed directly into your calculator in order to get your answer. All right. That's the whole point behind this, is that we just need to do enough work to get it to be calculator friendly. And then once we do that, it's all good. All right. So that being said, I don't want to have to type that into my calculator, so I'm not gonna. All right. So what I'm gonna do instead is pop a nice little juicy star on number 5 there, and leave that for you to try on your own also. So that's where we're gonna leave it for tonight. But the skills associated with number 5 are exactly the same as what we were doing in number 4. It's just you're kind of changing your perspective a little bit, but it's not difficult. All right. So that, as they say.